What science must our leaders understand? A very timely topic. If there are any future leaders in the audience, you might want to take notes. If you've been here all day or all weekend, you already know that our two speakers will be dividing their dialogue roughly into three parts. During the first half hour, they'll each present background information on the topic. In the second half hour or so, they will ask questions of each other. And the third half hour is your chance to step up to the microphones and ask questions of our speakers. Before I introduce our speakers, I'd like to thank Cal Physics Department and Wonderfest advisor Chris McKee for the department's generosity and hospitality in hosting Wonderfest here at Cal. Is Chris here? All right. Well, I'd like to thank him anyway. Wonderfest's mission is to make science and scientists accessible to the public. Together, Cal Physics and Wonderfest bring that mission to life each year. Our speakers this afternoon are Richard Muller, sitting at the far end, who is a professor in the Department of Physics here at Berkeley. His course, Physics for Future Presidents, was recently named Best Class at Berkeley in a student poll. Pretty good. He's also a faculty senior scientist at the Lawrence Berkeley Laboratory, where he's associated with the Institute for Nuclear and Particle Astrophysics. His research includes such diverse topics as the processes associated with impact cratering, the ice ages, patterns of extinction and biodiversity through time, and the proposal that our sun might have an as-yet undetected companion star. Professor Muller is also the prolific author of numerous articles, essays, and a handful of books, including the germane Physics for Future Presidents. And if you're a fan of the TV show Lost, he has recently written an article for Popular Mechanics describing the physics behind how Ben might have moved the island in the last season, which I thought was kind of interesting. So he did. He moved the island. Cool. And we also welcome Robert Siegel, sitting closer to me. Robert Siegel is an associate professor at Stanford University, where he holds appointments in the Department of Microbiology and Immunology, the program in Human Biology, and the Center for African Studies. Siegel's work focuses on viruses and infectious disease. He's in charge of the infectious disease portion of the required preclinical curriculum at Stanford Medical School. Professor Siegel is known for his innovative approaches to undergraduate education, including an intensive 12-unit sequence on viruses. His other academic interests include Darwinology and international development, and he has taught numerous courses in these subjects as well, both here and abroad. He's also the recipient of a ton of awards. I won't list them all because we'd be here all night, but just a few examples. He's a 3-time winner of the Henry J. Kaiser Award for Excellence in Preclinical Teaching. He's been awarded Stanford Medical School's Excellent in Teaching pin, and from Stanford's program in Human Biology, he's been awarded both the Master Advisor Award and the Award for Excellence in Faculty Advising. Now, please welcome our first speaker, Richard Muller.
Thank you very much. What I'm going to do is to very quickly, in, 20, 25 minutes, go through the key things you need to know to be President of the United States. I'm doing this very, very quickly, and if you don't follow everything, I'd at least like you to appreciate two things. One is I'm not going to say anything that you could not really understand if I really spent 20 minutes, an hour doing it instead of 20 minutes. And the other is that there's nothing I'm going to say that isn't absolutely important that you wouldn't want the future president to know. These are things you really have to know. So let me go through this quickly just to give an example. This is a course I teach. We spend a whole semester going through the material that I'm going to go through in 20 minutes. Okay, today's topics will be terrorism, nuclear weapons, energy, and climate change. Those aren't the usual physics topics, but there's a lot of physics in each one. So let's begin with terrorism. What do you worry about at terrorism? Well, a lot of people worrying about atom bombs. You also worry about atom bombs from rogue nations. Let me say a few quick things about atom bombs way too fast for you to even be able to take notes, so don't even try. There are two types of fundamental atom bombs that rogue nations and terrorists might get. One is the uranium bomb, the other is the plutonium bomb. Uranium bomb, very hard to get the purified uranium. Billions of dollars to purify the uranium. Once you have it, easy bomb. Even a high school student can do it. That's what gives rise to the story about that. The uranium bombs that we used to destroy Hiroshima, the different kind of bomb was used to destroy Nagasaki. That was the plutonium bomb. Purification is easy. If you happen to have a nuclear reactor, you can take the uranium out of the plutonium out of the nuclear reactor. Plutonium is manufactured in a nuclear reactor. You may not have a nuclear reactor, but North Korea does. Iran does. They can extract out the plutonium after they've run for a while. That's relatively easy to do, but then it's very hard to make a bomb. You need an implosion to make a bomb like that work. Very hard to do this. It's like squeezing a water balloon. Try to squeeze it and it comes out through your fingers. Very difficult to make. In fact, the one that was made by North Korea and exploded 2 years ago was a fizzle. Didn't explode very well. I'll come back to that in just a moment. The uranium bomb was the kind of bomb Saddam was making. Now you say, wait a minute, Muller's full of baloney. We know Saddam wasn't making a bomb. No, actually what you're doing is you're confusing the first Gulf War with the second Gulf War. At the end of the first Gulf War, we actually did go into Baghdad. Not we, the United Nations did. They found his facilities. The UN destroyed them. Here they are. This is a United Nations photo. You can find this on the web. Nobody disputes this. That Saddam was making a nuclear bomb at the end of the first war, and his facility was destroyed. The facility there is a kind of device called a calutron. None of the people in the intelligence agency were looking for calutrons because they hadn't been used since Lawrence invented them in World War II. It's shaped like a big letter C. He named it after Cal, our university. You normally don't hear this when you come to Cal. We don't tell you that the material that destroyed Hiroshima was based on a device that was named after Cal. But there was his calutron. He had enriched uranium to about 35%. He was 90% of the way there to making a bomb. It was all destroyed by the UN. Second time around, intelligence agencies figured he was doing the same thing. They were wrong. Second time around, he wasn't making a bomb. He just wanted us to think he was making a bomb. So that's an interesting little story. You got to know about these kinds of bombs to be a world leader. The North Korean bomb was made using plutonium from the nuclear reactor. We have these agreements with North Korea. We'll give you this technology if you allow us to inspect your nuclear reactor to make sure you're not extracting the plutonium. Once they cut off inspections, then they extract out the plutonium and they make a bomb. They did. It went off, exploded it 2 years ago. We detected it from the seismic shakes. They probably announced they had done it. It was actually quite a bit of a fizzle. The first bomb that we exploded, the test plutonium bomb in Alamogordo, was 20,000 tons of TNT. 20,000. Remember that number, 20,000. The North Korean nuke, which used the same amount of plutonium, was 400 tons. Not 20,000, only 400. It fizzled, probably because of some pollutant. In my class, we talk all about plutonium-240, how that gets in there, how it makes it pre-detonate. The implosion is very hard to do. Try squeezing a water balloon. See how much you can compress it. Comes out between the fingers. We don't know which reason it failed, but it did fail. North Korea had spent billions of dollars on this. What's my conclusion? It's really hard to make these bombs. If the North Korean nuke had been exploded in San Francisco, how devastating would it have been? There's the answer. The red circle shows it's about the same destruction as the World Trade Center. Radioactivity wouldn't last long either. It was such a small bomb. My conclusion now, so far I've just didn't give you the physics. Now let me give you my interpretation of this. My interpretation is we worry far too much about nukes in the hands of terrorists. The thing I really worry about in terrorism isn't that. It's the conventional attack. We talk about this conventional attack. The energy released in this conventional attack was 900 tons of TNT, almost a kiloton, more than twice the energy of the North Korean nuke. That's why I worry about this kind of attack. Where did all that energy come from? Here's a very surprising and important physics fact. Gasoline and jet fuel, they're very similar, contain 15 times as much energy as the same weight of TNT. A lot of people don't know that. That's why we use fuel air explosives during the Afghan war. Gasoline has this enormous energy. These airplanes, each airplane carried 60 tons of jet fuel. 60 tons. Multiply that by 15 to get the TNT equivalent, and it's 900 tons of TNT. North Korean nuke was only 400. With actually no risk whatsoever, they were able to release an attack more devastating. That's why I still worry about this as the kind of terrorist threat. I also don't worry much about dirty bombs. Don't have time to talk about that, but we can address it in questions if you're interested. Let's look at the energy program. A somewhat busy table, but let me just focus in here. There's TNT and there's gasoline. This is the energy in various different units. But look at the last column. It's relative to TNT. You can see gasoline has 15 times the energy of TNT. It's amazing. That's why we are so addicted to gasoline. It's not because we're in love with the smell of gasoline. It's because gasoline is very, very energetic. It's also convenient, and we used to think, or at least some people used to think, there was no pollution. After all it did was emit carbon dioxide and it went into the atmosphere. Nothing, no ashes left behind like with coal. We thought it was clean, or some people thought it was clean. One other thing I'll point out while we're here, let's look at batteries. Batteries compared to gasoline, gasoline has 100 times the energy. If you wondering why we aren't doing electric cars, there's some sort of conspiracy, well, the Tesla Roadster, which many of you may have heard about, gotten a lot of publicity, it carries 1,000 pounds of computer batteries. If you bought those retail, my battery here, weighs 1 pound, costs $120. If I bought 1,000 pounds of those, and they claim to be using ordinary computer batteries, it would cost $120,000 just for the batteries of the Tesla Roadster. Of course, they get them at a discount, buying them in such quantity. But the cost is really, really high. Moreover, these batteries, anybody who has a computer knows they only last about 3 years. Whether you're using them or not, they have a calendar life, all sorts of problems. It's a good reason why we're not driving electric automobiles. If you want to make a plug-in hybrid, if you think this is the future, before you convert your car, calculate, find out how many recharges the battery will take, and find out what the expense of replacing the battery is. The main expense in a plug-in battery is not the electricity. It's replacing the batteries after 3 years. Cost of energy. I have some of the things there. Electricity from batteries. Oh, look at this one down here is amazing. We spend 10 cents per kilowatt hour for electricity. That's the fourth column there. If we buy it from AAA batteries at 7-Eleven, instead of 10 cents per kilowatt hour, it's $1,000 per kilowatt hour. Isn't that amazing? There's such imbalances in the energy. That's because you can't run a flashlight on gasoline. It's because electricity, we don't have cars that run on coal. If we did, we'd be using it. So we get somewhat tied in. Cost of energy is, so there's the $1,000. Let's talk about how much fossil fuel we have in the United States, in the world, various different countries. Think of what country has the largest reserves of fossil fuel. Let me show you the chart very quickly. The US has the largest reserves of fossil fuels of any country in the world. There it is up at the top. I've included oil, coal, and gas. Wait a minute, what about Saudi Arabia? Well, they're down here. There they are, Saudi Arabia right there. They have the most oil, but they have very little coal, not much gas. The US has huge amounts of coal and actually a lot more gas than is shown right here, as T. Boone Pickens loves to point out. We have these huge amounts of fossil fuel. That's good news and bad news. And you have to keep these issues straight. It's good because it means we can have energy independence once we switch to coal. And coal can be converted to gasoline. It's bad because fossil fuels produce carbon dioxide, and that's responsible, 90% chance, very likely responsible for much of the global warming we've been observing. So, keep these two issues separate in your heads. There's energy independence. You hear a lot about that from the Republicans. There's global warming. You hear a lot about that from the Democrats. They both relate to energy, but they're different issues. Energy independence means not sending money to the Middle East to fund the terrorists. Global warming means not burning fossil fuels to increase the carbon dioxide that makes greenhouse warming. They are both energy issues, but sometimes they're in conflict, sometimes they're not. When we're talking about coal, we're talking about energy independence. When you talk about clean coal, you're talking about addressing both issues. When you're talking about solar, you're talking about both issues. But when you're talking about, and likewise for conservation, sometimes though you're talking about only global warming or about energy independence, though both energy issues, you've got to keep them straight. Let's talk about global warming. There's the record for global warming. This is the main reason that most of us believe that global warming is true. This is the temperature back in the, before the 1900s, and the temperature began to go up. You need to know the initials IPCC. Just like you need to know the initials UN. The IPCC, if you don't know those initials, be a little bit embarrassed right now. I'm not going to ask you to raise your hands. It stands for the Intergovernmental Panel on Climate Change. You don't have to know that. You just have to know IPCC. IPCC won the Nobel Prize last year, the Nobel Peace Prize. They are the scientists that made the consensus on global warming. What I'm going to be telling you about global warming is not my opinion. It is the IPCC opinion. I don't agree with them on everything, but let me give you their opinion because that is the consensus. You will be surprised at what the consensus is because you rarely hear it. People are always exaggerating on both sides. They'll say, oh, you can't trust them, or they'll say, oh, they're underestimating it, or something. They'll give you their own opinion. I'll tell you what they're really saying. This is global warming. What they say is that the global warming that took place from 1850 up until 1960 or so could very well have been totally natural, coming out of the last ice age. This is the IPCC. This is not me. From 1957 on, they say some of this global warming is very likely caused by humans. The reason is our carbon dioxide kept on going up, and the solar activity that probably accounted for this began to go down. So this is the global warming. How much is that? It's about 1 degree Fahrenheit, 0.8 degrees Fahrenheit. If you believe you have sensed global warming yourself, keep in mind it's only 0.1 degree Fahrenheit. 1 degree Fahrenheit, 0.8 degrees Fahrenheit. This is global warming. Why do we worry about it? Because we're worried that it's going to be 5 degrees Fahrenheit, 6 degrees Fahrenheit within our lifetimes. That's coming up. The IPCC gives 3 bits of evidence for global warming. There's the temperature record, 1957 on. There's the rise in sea level. This is the rise in sea level. The part that's due to humans is from 1957 on. That's this part here. Notice the entire rise in sea level is about 20 centimeters. That's 8 inches. About 4 inches of sea level caused by humans. Those are the numbers of the scientific consensus. The other bit of evidence they give, and this is the melting of ice in the Arctic. So here we have the ice in the Arctic. This one is, I guess, 1979, and here it is 2003, and you see there's less ice in the Arctic. And that's the third bit of evidence. Based on this and based on calculations that go back to 1896, we expect global warming to really rise very substantially, as I said, 5 degrees Fahrenheit in the next 40 or 50 years. So this is what's coming. I blocked this part out. I actually played a role in discrediting the previous interpretation that it's the warmest it's been in 1,000 years. We now know, in fact, it is the warmest it's been in about 400 years. When I say the warmest it's been, let me point out some things that are important about that. Here is that record again, but now I want to focus in on the last 10 years. Think of events in the last 10 years that convinced you that global warming is getting worse. Let me show you the record. I download this every month from 2 different sources. One is the United States, the other is in Britain. These are the records used by the IPCC. Here's the latest. This is the last 10 years of global warming. And 2 different records. One is NOAA, the other is the UK Met Center. You may notice the warmest record on temperature was 1998, 10 years ago. You may notice the temperature seems to be going down a little bit. That's true, it's gone down in the last 10 years. Does that mean global warming isn't real? No. These things have fits and spurts. And the fact that it goes up and then levels off and goes up and levels off doesn't mean the trend isn't up. But the last 10 years it's been down. If you think that the fire on Angel Island is due to global warming, you're fooling yourself. You're confusing weather or maybe local climate with global warming. We haven't had any warming in 10 years. Doesn't mean it's not real. It is real, and I'm really concerned about it. It's very likely caused by humans, and we better do something about it. But don't confuse anecdotes, stories, things you see. It rained yesterday, but not today. Ah, it must be global warming. Don't confuse that kind of stuff. Let me give you, the IPCC says, and here's their quote, that climate change in the past 50 years is very likely. That means 90%. That means there's a 10% chance it's not caused by humans. Pray that that's the case, because we're not going to do anything about it, not that I see. I don't see any of our political leaders doing anything that's going to work. I'll come to that in a moment. What am I doing? Okay, I have 5 minutes to go on my own 20-minute schedule. So this is what the IPCC says. This is the scientific consensus. Okay, why do they say there's some chance that 10% chance that humans aren't causing it? It's because cloud cover is so uncertain. If cloud cover increases by 2%, it's so much reflection that would completely undo global warming. IPCC doesn't think that's the case. They say there's only a 10% chance that that's the case. What's going to happen? The predictions go way back to 1896. Arrhenius in 1896 said, if you have double the carbon dioxide, the global warming, the temperature will go up by 3 degrees Celsius and 5 degrees Fahrenheit. It goes back to 1896. It doesn't depend on complicated computer calculations. It really doesn't. Those agree with the things going back. So a series of books and things pretty much understand global warming. The big uncertainty is whether cloud cover will increase as more water evaporates. Anecdotes. I said, you think of the burning of Angel Island, that must be global warming, and then you learn it hasn't warmed in the last 10 years. Let me give you a series of anecdotes that the IPCC, the consensus, does not pay attention to, but the popular media does. You should know that these are not part of the argument. These are picking examples. You find something bad in the weather and say, global warming. But that's not science. Scientists have to be more careful. Here's the first one. This is not in the IPCC report. Forgive me for this one. Let me give you another anecdote. Hurricanes. Hurricanes are increasing, right? Everybody knows hurricanes are increasing. Hurricane Katrina was due to global warming. Here's the problem. If you go back in time, we never used to find hurricanes out at sea. Now we do. Much of the increase of hurricanes is because we have satellites and buoys out at sea now that detect hurricanes. Suppose we pick an unbiased sample, hurricanes that hit the coast of the US. Those are always observed, always recorded. Here's a list, you can get them from the World Almanac, hurricanes that hit the coast, and you'll see they're not actually going up. In fact, there's a slight downward trend. What about the more violent ones? Well, there's a slight downward trend in the more violent ones too. Those are the light gray. Hurricanes are going down. How do we sync that with global warming, which I say is real? Well, the answer is global warming occurs more in the poles than in the south, and you get hurricanes because of temperature differences in the equator versus the poles. And so it's plausible that hurricanes will go down. That doesn't sound frightening. And it's possible that they'll go up too. And you'll see the IPCC will say. And it's conceivable that storms will increase. This gets quoted in the newspapers as, if we have global warming, storms will go up. But that's not what the IPCC says. There are other things too. This is the cost of hurricanes. That's been going up. Well, Al Gore shows a plot like this one. He says the cost of hurricanes is going way up. He doesn't even use constant dollars. He doesn't compensate for inflation. He compensates for inflation and for the increased cost of houses. People didn't used to build houses at the seacoast because hurricanes would knock them down. If you compensate for that too, you find the cost of hurricanes isn't going up, which it shouldn't, because the number of hurricanes hasn't been going up, nor has the intensity. What about sea level? I showed you the sea level plot. Sea level is going to go up. This is the consensus. The consensus is it will continue to go up. And here's 2100 right here. And you see it's going to go up by maybe a foot or two. What about these movies about the flooding of Florida and the flooding of New York? Listen to them. When they announce them, they'll say, if Antarctica were to melt, or if Greenland were to melt, then you would see these movies. But the consensus is that they're not going to melt. The speakers don't lie. They always put an if in there. The consensus is, no, the flooding is not going to be a problem within the next 100 years. Maybe within 1,000 years, here, it'll be a serious problem, but not for the next 100 years. So this is the consensus. What about the melting of Antarctica? Well, the melting of Antarctica, unfortunately, was predicted. The IPCC looked at this in 2001 when they knew the satellites would measure the ice in Antarctica, and they concluded that due to global warming, the ice in Antarctica would actually increase. The reason is Antarctica is only warming by a degree or two. It's still well below freezing. More moisture from the oceans will cause ice to build up. It's exactly the opposite of what's been seen. The scientists who made the report, in fact, pointed out, they say, the IPCC in 2001 predicted the Antarctic ice sheets would gain mass. It didn't. You don't hear this report as evidence against global warming, because this is probably due to some local effect. I mean, global warming, there is compelling evidence that global warming is going on. But if you start picking anecdotes, then you have to pick the anecdotes that go against it too. So they don't get into that business. They just pick the really strong evidence and present that. But that doesn't convince the public. The public wants to see the dying polar bears and so on. And so beware of that. Beware of people who give you these anecdotes and try to convince you. Is Alaska melting? Well, it's kind of peculiar, because although the line is usually driven for Alaska melting as diagonal, in fact, the North Sea shows what's called a regime change. It went up suddenly. There hasn't been any warming in Alaska for 20 years. Here's a plot I got just last month of the yellow is the temperature in Alaska this year. The blue line is the temperature average over the last 20 years. Alaska isn't warming anymore. It's warmer than it was. But it looks like it warmed in 1979, 1980, and then it stayed up there. It's something peculiar going on up there. This is why the scientists, the consensus doesn't take the melting of Alaska as evidence, but it sure makes you get to see these drunken trees and things. Okay, are the wildfires going up? No, they're actually going down, despite what you'll hear in some famous movies. Are the tornadoes going up? No, they're actually going down. This is all consistent with global warming, but it's not as frightening as it is. This is global warming. Okay, now what are we going to do about it? Now we get to the hard part, and I'm just about out of time. The time I allocate, I'll give myself an extra 2 minutes. What are we going to do about it? Here's the problem in a nutshell. The United States has been responsible for more than its fair share. Look at that. That's the US. More carbon dioxide than even all of Europe put together. So out of that 0.8 degrees, the United States contributed 0.2 degrees Fahrenheit of global warming. In the next 50 years, we're probably going to contribute another 0.2 or maybe 0.3 degrees Fahrenheit. Are we worried about 0.2 or 0.3? No, we're worried about 5 degrees. But what if the US cuts back to the Kyoto levels? Well, if we cut back, then we'll cut back, boom, like that, and stay here. That's really good. But the other countries, if they don't cut back, will make up for that in 3 years. If we reduce to the 1990 levels and cut back, we will delay global warming by 3 years. It will still happen inevitably. The reason is that most of the carbon dioxide these days is coming from the developing countries. There's another plot that shows the developing countries, the so-called non-OECD. This is the OECD. This is where global warming is going to come from. If they don't cut back, we will have global warming. It doesn't matter what we do in the United States. It doesn't matter if you drive a hybrid. I do. I have screw-in fluorescents. I'm not going to do anything. It won't help. We only did 0.2. We're only going to do 0.2 in the future. We can cut back and feel good, but unless we can control the carbon dioxide, and they have every right to emit this carbon dioxide because they're poor. So we can't tell them, stay poor and don't emit any. No, we have to encourage them to get wealthy. So what do? Conservation is the biggest issue. These are screw-in fluorescents. This is a photograph I took in Notre Dame Cathedral. And those are screw-in fluorescents. If you think they're not beautiful, take a look at Notre Dame. There are lots of things we can do. Anybody who argues with their neighbor over which is the better way, solar versus nuclear, versus conservation, stop those arguments. We need all of those. Unless we have a full rainbow, a full spectrum, a full bunch of wedges of every possible way of cutting back, and unless these things are affordable by the developing world, it's going to save us 3 years, and that's it. So fortunately, the most polluting countries per dollar of GNP are China, Russia, India, South Africa, and so on. The US is actually fairly good. That's because they're developing countries. Developing countries, the US did this, always has more pollution per GDP. So to step aside from the physics now, give personal opinion, I think the only way we're going to do this is we have to pay for the developing countries. We have to basically put the money in to make them efficient. They shouldn't have to. They're developing. They have every right to be as wealthy as we do. I'm optimistic about the long-term future because the birth rate's going down faster than the death rate. And in 2050, almost every expert agrees the world population is going to stop growing, so we're okay on that. There's such a thing called clean coal. Obama gets a lot of flack for mentioning clean coal. They say it's an oxymoron, doesn't exist. It really does. Clean coal means you make electricity from coal. When the carbon dioxide comes out, you put it underground. You bury it underground. You can do that. I can talk about that at length. Solar is coming along very fast. But expensive solar doesn't do any good unless it's cheap enough for either China to use it or for us to buy it and give it to China. China, India, the developing world, that's where the global warming is coming from. So expensive solutions, electric automobiles, unless they're cheap electric, cheap batteries, they don't do any good. Wind is a good thing. Take a look at those two pictures. There's a wind turbine, and there's the Statue of Liberty, and they are to the same scale. Wind turbines these days aren't the old windmills of yesteryear. Okay, so let me wind up. What do we have to do? Public needs to know this stuff. I think you agree there's nothing here I said that you don't need to know. There's nothing here that you don't want the future president to know. I would love to see the president say, okay, tonight, now that I'm president, put partisan physics aside, and tonight we're going to discuss the nonpartisan physics that you may believe in trickle-up economics or trickle-down economics. Fine, that's your choice, but let's discuss the physics. Physics is nonpartisan, we can agree on this. And sorry I had to go so fast. I would love to see the president do that. I did write a book on the subject, It was written specifically addressing the next president. I didn't call him by name because I didn't know which one would win, but it's actually written for only one book. But if you want to know what the president needs to know, you can always get a copy of my book. So I will, and that's my website. All my lectures, by the way, for my class, Physics for Future Presidents, are available online. You can listen to them. 2 years of lectures, 4 different sets. Pick the one you want, and they're all video casts, so you can watch that. So I ran over a little bit, but your turn. Don't move.
Okay. Sorry about that. I toggled the wrong thing, so it's now going to hibernate. Anyway, in the meantime, while my computer goes to sleep, I think that's appropriate given the fact that you guys just heard Dement talk, and he talked about the importance of sleep. My computer's obviously taking a power nap. I want to begin by thanking Tucker for putting this on. It's really quite remarkable. And I want to thank the stalwart among you who came here. I actually used to teach high school, but I decided to get an easier job teaching college students. But since I was here for Bill's talk, and he was taking a walk down memory lane, I decided that I would take a walk down memory lane also, because actually I took that class from him, and I went on to TA his sleep class. I cut my teeth on undergraduate research, doing sleep research with Bill Dement. And then as turnaround, his son was my advisee and went on to TA my class on virology, actually, molecular biology. So that was kind of fun. And then my brother's here, and he's actually he's a dreamologist and has written books on the topic. So it was nice of him to pop in. Now, while this is still coming up, let's see. There we go. I think we're functioning. Now, if Tucker had given me the topic to talk about genomic replication of retroviruses, or perhaps viral taxonomy, and by the way, you probably should all know that when I started teaching 20 years ago, there were only 7 known families of viruses, but now there are 24. Or smallpox eradication, one of the great success stories in the history of science, or even the transition from CD5 receptors to CXCR4 receptors. That's the major event that signals the downturning of health in people with HIV. That would have been easy. But instead, Tucker, Darwin bless him, has asked me to talk about, basically asked me to philosophize. Okay, so here we go. So I'm going to talk about science. And I have to say, what? Okay, well, there's more coming, so it's okay. Genius may have its limitation, but stupidity is not thus handicapped. What science must our leaders understand? So we just heard some compelling information about physics. Actually, it was sort of a feel-good talk about global warming in a way, since you made it sound like it wasn't as bad as I thought. I'll have to ask you about that. But I'm going to tell you that basically, if I were going to say one thing, it would actually be that they should know about viruses. Microbes rule. Half of everybody who, in the United States, the proximal cause of death will be an infectious disease. Okay, it won't be global warming. Although global warming will directly contribute to infectious disease, although population growth is probably the thing that's going to contribute more to global warming. So we'll talk about the complex web that's involved in all these things. And if we were going to talk about major impacts on human populations, there's nothing that had a bigger impact than the 1918-1919 influenza epidemic, which killed between 20 and 50 million people in the course of 2 years. So if he should know anything, he should know about microbiology, of course. Okay, whatever it is, it's very, very little. You can't even see them. Nobody even knew about them until fairly recently. Okay, so in turning this question, asking me to talk about philosophy, he's sort of asking me what leadership must our scientists understand so they can talk about this stuff. Okay, and I'll turn to Stephen Jay Gould, who says, scientists have power by virtue of the respect commanded by their discipline. We may therefore be solely tempted to misuse that power in furthering a personal prejudice, which I did just now, or social goal. Why not provide that extra oomph by extending the umbrella of science over a personal preference or in ethics or politics? But we cannot, lest we lose the very respect that tempted us in the first place. And I actually disagree with Gould. In fact, I disagree with him most things. But I think we have to use our knowledge of science actually to help influence policy. Okay, so I posed this question. I decided I would do a Thomas Friedman. And so I'd ask my kids, what science do our leaders need to understand? Okay, so first principle is that you must not fool yourself, and you're the easiest person to fool. Okay, so I think we should be more explicit in step 2, that a miracle occurs. Okay, so when I ask that question of my kids, in fact, when I ask it to a lot of people, they tend to answer the question as how much science should our leaders understand, which I thought was kind of interesting, a slightly different question. And so my 14-year-old said, well, they should know at least up to the high school level, which of course most of us don't remember science up to the high school level, so I thought that was pretty good. And then I asked my son, who's a physics major at Columbia, and he said, as much as possible, okay? So I'll get back to that. And then a friend of mine who is an expert on infectious disease, we talked about how much infectious disease should a doctor know, and he said they should be encyclopedic. You want your doctor to be encyclopedic. And I thought that's probably a comment you might make about your leaders as well. So anyway, but there's so much information. How are you going to master it all? Okay, this is... Okay, so in fact, if we just took medicine, to cover the vast field of medicine, this is from 1905, in 4 years is an impossible task. We can only instill principles, put the student on the right path, give methods, teach how to study, and to discern between essentials and non-essentials. And that's essentially the tack that I'm eventually going to take. Okay, so, but my answer, at least as far as quantity is concerned, is that he should know a hell of a lot more than me. And I only have 2 doctorates. Because I'm not running for president, and I don't have to make the important decisions that he's going to have to make. I'm saying he, because that's probably likely. Okay, so this is the discoverer of vitamin C, one the Nobel Prize. Discovery consists in seeing what everybody else has seen and what nobody else has thought, which I think is really beautiful. So, and then I asked my oldest son, who graduated from Cal with a degree in math and economics, and he said they should know enough to make intelligent policy. Okay, and so what is he doing? What is he doing? What is he doing? What the hell am I doing? Okay. Okay. So, but do they really need to know all these things, or can he just the next president can just call up Richard and say, "Listen, Richard, we have a problem. I've heard about this thing called global warming. Can you tell me about it?" So, does he really only need to recruit an expert? Okay. Shall I refuse my dinner because I do not fully understand the process of digestion? So he doesn't need to know it. In order to drive a car, you don't need to know everything there is to know about a car. Okay. Or does he only need to know how to recruit the people who recruit the experts? Ad infinitum. Okay, so I'm going to give you a doctor analogy. I think that if you're a physician, or if you're going to go, you're worried about going to the doctor. So we'll say that the president is going to be the guardian of the health of the country. So what should he know? Okay, so, well, in terms of looking at the health of the country, he's not going to be the doctor. Okay, so even if you're not the doctor, you still, as a patient, if you're going to recruit the expert, you still have to be quite knowledgeable. You can't be completely ignorant and just go to the doctor and say, do something for me. What does the patient need to know? Okay, first of all, the patient needs to know which experts to choose. Okay, and whether they choose one group of experts or another, they're going to get a very different answer. If we ask Dr. Dement, what's the most important issue, the answer is sleep. Okay, if we ask Dr. Muller, what's the most important, it's physics. If you ask me, it's obviously infectious disease. Okay, so choice of experts is important. Secondly, you have to be knowledgeable enough to understand what's going on. So you have to be able to make the decision in the way that you would have informed consent. You also need to understand warning signs. What kind of illness is arising? What are the things that I'm worried about? You need to be able to do self-exam to be able to look for things. You need to be able to do screening tests also to find stuff that may be invisible now. It may be something that's building up, but the sooner you catch it, the more likely it is it's going to have a salubrious outcome. And you need to know where to look for information. So these are the sorts of things that the president would need to know, even if he's not expert in global warming or in the pathogenesis of rotavirus. And he needs to be able to institute preventive measures to prevent these diseases from happening even before they get started. Okay, so now if we think about what do our leaders need to understand, one thing is content, and that's the first thing that a lot of people think of. We just heard a bit about what the content is, global warming. Richard probably could have gone for a whole quarter and told us the content. So first get the facts, then you can distort them at your leisure. Okay, so what content, let me just take a quick poll. What are, you guys are all experts, what is some of the content that you think the president needs to know?
Avian flu.
Sociology, avian flu.
Global warming.
Global warming.
Nuclear.
Economics.
How to get elected.
How to get elected? Okay. Okay, so it's possible to store the mind with a million facts and still be entirely uneducated, or as Poincaré says, science is facts just as houses are made of stones, so is science made of facts, but a lot of stones is not a house, and a collection of facts is not necessarily science. Okay, so global warming, I think global warming is really important, but I think global warming is actually a downstream effect of other things. And so if we really wanted to understand global warming, we'd be asking, what's going on upstream, and we'd be dealing with those problems. Okay, so again, it's a matter of perspective, global warming. This is the Canadian perspective, Canadians for global warming. Canada leading the world and being just north of the United States. Or just south of Alaska, I guess now. They could level with me, doctor, how high is my fever? Okay. So, but again, there are other issues that we're not talking, they're not even on the table. By the way, just think how many science questions that were asked. They asked during the debates, virtually none. This is what happens when bird flu meets measles, okay? This is what flu, the effects it can have on you. My students make three-dimensional models, and this is even more dramatic effect. And I don't know if you guys are aware of HIPAA laws, so HIPAA laws. The leader should know something about evolution, about biology. Okay, do you believe in evolution? As long as it's between consenting adults. Okay, so here's the public view of the way biology works. These are mutants. This shows you that a small change can actually have a big effect. So these are the collected walks of William Shakespeare. Or perhaps his muscles went into spam. Okay. Yeah, there's a whole book of those. Okay, so what should our leaders understand? They should understand the purpose of science. I have a whole long list, which I probably won't get to. So what are the goals of science? We've been focusing on science as problem solving. We also need to think about science as possibility generating, and we need to think about science just for science's sake. Science is almost like art. It helps us understand the world. It's beautiful. I laugh every time somebody says, well, the more we understand, it'll take away the beauty. There isn't a scientist out there who doesn't feel that they have a greater appreciation for the beauty of the things they study when they learn more about them. If you know more about it, if you look closely at a flower, it's much more beautiful. So the notion that science is going to destroy our appreciation of the world is just, it's laughable. So these are actually applied parts of science. And then the other thing is that's been thrown by the wayside are basically knowledge for knowledge's sake. So pure science. And that needs to be needs to be funded as well, because if we all now depend on things like MRIs, which are related to quantum physics. Now, when quantum physics first came out, people were probably thinking there will never be a use for this. This is just crazy. Okay, so now nuclear magnetic resonance actually is something that's very important to your future health. And then this is biology as beauty. This is actually a single strand of DNA looked on end on. Okay, so at the molecular level, this is a photograph using electron microscopy of DNA. This is called atomic force microscopy. You can actually see the double strand in DNA. You thought that was all like hypothetical, and that's a close-up. You can see how it twists. There are 10 turns, 10 bases per turn, and this is what it looks like end on. So it's really quite beautiful. These are just models of it. And then we hear about Proxmire Golden Fleece Award, and somebody says, well, listen, they spent good money to figure out the genetic makeup of fruit flies. Okay? Well, basically, some of our key understanding of genetics and what we know about biology comes from studying fruit flies. Or somebody was studying a gene that actually causes microorganisms to light up. That was the subject of this year's Nobel Prize. Okay, so it's important not to distort the science, because a lot of times you can make things that are very important seem rather silly. On the other hand, there's plenty of science things that we fund that probably shouldn't be funded, but it's difficult to know at the time. Indiana Jones, nothing shocks me. I'm a scientist. Okay, so in fact, one of the things that concerns me most is partisan science and pork barrel spending. So in fact, what we really need is to work on some of these big issues, but not just applied issues, because we need to think about what's going to come along in the future. Now, we also need to talk about the nature of science. So what is the nature of science? Okay, here we have, I think we're making progress, running around like a goat, fish. Okay, anyway. Okay, so the nature of science, and I just threw some things on the list. This is other people could make this list up. Science should be empirical, it should be predictable, it should be reproductive, it should have external validity, it should be consistent with other facts. These are things that our leaders need to know, is that science is not like, I think this is the case. Science is, we take the data, we look and see what global warming is doing, and then we make a decision based on the information. Okay, so what are some of the big problems in science? Okay, so we talked about some of them. Okay, now, I should say, now, the big problems in science have all been solved. Okay, we understand gravity, we understand atomic and subatomic structure, we know about the nature of energy, electromagnetism, and other forces of nature. We know about evolution. We know the genetic code. We can even manipulate life. We have sequenced the human genome. People thought that would never be possible. We know events that happen milliseconds after the beginning of the Big Bang. We've developed incredible computers and global communications. We know about plate tectonics and the structure of the Earth. We know about quantum physics and relativity. We basically, all the big problems and solve them. Now we're just going to fill in the little details, the gaps. Okay, how many people think that's true? Well, you know where I'm going for, but the fact is, most scientists believe that's the case. Most people in the world believe that's the case. I'm surprised that nobody raised their hand. And when you talk to people like in medicine, they say, well, how come we don't know this issue? Okay, where are the big issues that are coming tomorrow? By the way, the reason, my argument about this is that if we were going to look, for instance, at global warming, we see this little rise. If we were going to look at our knowledge about science, straight up. Okay? It's incredible the amount that we've learned within the last 5 years, 10 years, 20 years. It's still going on. Now, where is the future of science going? Okay, what are the big issues that we're going to discover in the future?
Consciousness.
Consciousness, okay. Dark matter, okay.
The time arrow.
The time arrow.
Protein folding.
Protein folding. Good ones. Okay. What?
Immune diseases.
Immune diseases. Okay. I contend that we don't actually even know what the issues are, because science is in its infancy, and a lot of those issues are ones that we just recently defined as issues. Okay, if we think about what we've learned in the last 200 years, how about if we survive this whole thing? How about in the next 200 years? What will we know? What will our computers be able to do? What will our medicine be able to do? What will our science be able to do? What about in 2,000 years? Okay, so where is science going? Yeah.
I was just going to say, maybe one of the things we would know is how to bring more of the scientific method into politics and government.
You're dreaming! Okay, so what do you expect? 90% of scientists who ever live are alive today. Okay, so. And then as physicist, John Wheeler said, we live on an island of knowledge surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance. Okay, so bless you, take care of that viral infection. Okay. We now understand the process of science, a bit about science methodology, how science works. Science has really changed. The whole idea of the scientific method has only developed within the last 150 years in its current form, and the idea of doing controlled tests is actually probably less than 100 years old. Science is brand new. Okay? Now, people did trial and error stuff. We learned stuff over a long period of time, but it went very slowly. Now we have methodology for looking into issues. Okay. As you know, we put sardine genes in potatoes and potato genes in sardines. The results are in. We won't do anything like that again. Okay, so here are a bunch of vertebrate limbs. Okay, so why do you? Now, where's the? Oh, here it is. Okay, so the creator wasn't very creative. They have the same bones, okay? I don't, it's kind of interesting that they have a single bone in the upper limb and two bones in the lower limb. It's true for it's true for your arms or your upper limbs and your lower limbs. So one bone, two bones, it's all the way through. Same thing everywhere. We can do the same thing with vertebrates. The common question, probably everybody knows the answer now, is how many vertebrates are in the neck of vertebrae are in the neck of a giraffe?
The same.
Okay, the answer is the same. It's 7, but the answer is the same. Okay, not very creative. Now you look at this and you say, what's the explanation for this? Okay, the explanation is they had to have arisen by a common process. That's really the only explanation that makes any sense. So science has to do with looking for reasonable explanations. This is the genetic code. Now, if this was made by the creator had an incredible sense of humor because this is incredibly quirky. Okay? It makes a lot of sense. There's some logic to it. If you make a mistake in the third position, it doesn't change the amino acid you put there, and nothing happens to you. But then there's other things where, for instance, you get this encodes one amino acid, and then way down here you encode another amino acid. Okay, it's quirky. Some amino acids have one thing that encode them. Some have 6 that encode them. By the way, one of my pet peeves is what you read in the paper all the time. We've just determined the genetic code of gorillas. Okay, well. We actually determined the genetic sequence. I actually know the genetic code of gorillas. It's this. In fact, I know the genetic code of platypus. It's this. I know the genetic code of bacteria. It's this. I know the genetic code of plants is this. So that's one of the powers of science, is to be able to make predictions. Now, I haven't sequenced lemurs, okay, but I know that all living things have the same quirky genetic code. So this is just another example of that. Okay, science, the way science occurs is it doesn't always move straight ahead. Sometimes it's a hunch. Sometimes it's a fashion. Sometimes we have to go with that. Imagination is more important than knowledge. I don't know if I agree with that, but imagination is very important. The leaders need to understand the complexity of science. So science occurs at many levels. This is illustrated again by infectious disease. Great fleas have little fleas upon their backs to bite them. And little fleas have lesser fleas, and so ad infinitum. And all the great fleas themselves, in turn, have greater fleas to go on, while these, again, have greater still, and so on. Okay? The leaders need to understand that science is interdisciplinary, that these things don't exist in a vacuum, even though sometimes we study them in a vacuum. Here's chemistry for geologists. These are... The leader should understand something about the structure of science and how it's broken up. And I'm just picking a few little aspects of this. One thing is the notion of big science. Now, big science was just invented recently. Science is new, but big science is even newer. The first real example of big science was the Manhattan Project. A lot of big science occurs in the military and in government. One very, very successful example of big science was the sequencing of the human genome. Now, the government paid for that. Did that mean that industry lost out? No. It spawned all kinds of industry. I think we're missing the boat on a lot of big science that might actually be useful for generating batteries that are more efficient, or generating cars that can actually run on without producing carbon emissions. Why do we have to leave this to the vested interests of the oil industry and the car industries? It'll spawn plenty of business if we actually do it as a cooperative exercise. Okay. So what are some other issues for big science? Vaccines, fuel efficiency. Okay. The leaders should understand the implications of science. What does it mean when you get something? And the implications, both in terms of the good and the bad of science, can have powerful effects on the world. By good and bad, I mean that science can produce things that are dangerous, but science can also avert dangers as well. It depends on how we use science. They should understand the relevance of science to our life. It's so interesting that I grew up in the post-Sputnik era, in which science was fashionable, science was important. We knew that we were going to have our dominance in the world on the basis of science. Now we want to be Joe Sixpack. It's the dumbing down of the United States. And so the leaders have to understand the importance of science in terms of the success of the country. Leaders need to understand enough about science to be able to generate policy, even if it's only by getting experts to consult with. Okay. Anyway, don't let worries kill you. Let the church help. Okay. Okay. So they need to, in generating policy, they need to be able to focus on the relevant. Okay. So caution. This sign has sharp edges. Okay. Also, the bridge is out ahead. Okay, and this, I actually took this in Uganda. In Uganda, okay? They're worried about golf balls. Oh my God, that's great. Okay, so we have to worry about vested interests. And they need to be able to know enough about policy to make important fiscal decisions. Albert Einstein in his later years was unable to figure out why, if he was so smart and so famous, he wasn't rich. Okay? Okay, and once you do transmute lead into gold, you'll find the market for it is very speculative. Okay, so are we only seeing part of the picture? That's the other thing, or a moment in time? Okay, so I actually caught this. Walking by. And then we have to ask, is science going to be reactive or proactive in terms of what we're going to do for the future? So we're focused, I think global warming is a huge problem, and we need to do something about it. We heard, if you were here at Stanford yesterday, you heard Dr. Chu talk about the Titanic analogy that we're going to hit the iceberg, but the question is how hard are we going to hit it? But I think what we're not doing right now, because we're so obsessed with these problems, is looking for what the other problems down the road are. A lot of problems are like cancer. They build up, and if you don't actually look for them, they present themselves when it's far too late. The leaders have to understand about the globalization of science in the world. And so here are some of the global challenges that science faces. Problems of disease, pollution, global warming, loss of species diversity, loss of cultural diversity, economic instability, overpopulation. And in fact, I think the country concept is basically archaic. And so companies have realized that. They have international companies. Diseases have realized that. They don't actually have to check their visas at the border. And so we're going to find out, neither does pollution. So we're going to find out that this notion of thinking about ourselves as a nation is actually outdated. And I think the thing that's underlying many of these problems is actually overpopulation, and most people don't want to talk much about that. So we're actually ignoring the problem. So things are fine right now. Okay. And lastly, I want to talk the leaders should be able to know about the importance of education, science education, in terms of the future of the country. The aim of education is not knowledge, but action. So we also need to replace fear with knowledge. Okay, so here we have education. Okay, so I'll end at that point. All around me, I see nothing but chaos, panic, and disorder. At last, my work is done. Okay, thank you very much.
Thank you very much, Professors Muller and Siegel. Now let's have some questions from the audience. There's a microphone up there and one down here, and you can line up behind them. Go for it.
I had a question for Dr. Muller. There was some physics in your talk that I have a physics background, and I sort of didn't mesh with. There's a lot of discussion about global warming and the fact that it should cause a temperature rise. And if you have a pan of water on the stove and you put some ice in it, the temperature of that pan is not expected to rise, because the additional energy goes into melting the ice. And given the fact that we don't really know a lot about the temperature of the deep ocean and lots of places in the world, the amount of phase change that we're going to have is not. I mean, we just have a lot of unknowns, it seems, with global warming. I guess the underlying question was, given the fact that there are so many unknowns, does proceeding, I mean, one of the things I would love to ask our leaders is, do we want to, I mean, a lot of this has to do with risk management. And it seems like one of the questions is, do we want to, like, how do we manage the risk, and how do we choose? I mean, to me, it seems like we're guessing that we're going to get lucky.
Okay, let me ask.
Sorry.
Is my mic on now? Okay. I actually disagree with your premise. You say the world is so complicated, we can't really be sure about global warming. We don't know the distribution of temperatures in the ocean. We don't know how they flow. Actually, many people have looked at that with a great deal of care. And my evaluation is that what they've done has really only one unknown left, and that's the cloud cover. So that's the unknown. It's scoped with. I disagree with the IPCC a little bit, but part of the reason we believe the calculations is that back in 1896, Arrhenius made these calculations on global warming, and we're right on track. We're just about what he calculated. As time has gone on, we've improved our calculations. Arrhenius didn't know how to handle the distribution of mass. He had some very simple calculations in 1979. We did some much more detailed calculations with much better differential equations, basically verified that he was right. Now the computer models are basically verifying that what we did in 1979 are right. I think we really understand most of this, with the one exception of whether the water vapor will cause increased cloud cover. So I think right now, the IPCC says 90% confidence. Maybe that's a little bit overblown. And the issue is risk, certainly risk management. I think the risk is very high, though. If I said 90% chance that terrorists is going to come into this room and blow it up in the next half hour, you wouldn't say, well, 10% chance, that's okay. Actually, I think it's a 30% chance, so maybe it's not so bad. The other problem is that carbon dioxide leads to acidification of the oceans. That's absolutely much more straightforward. That's not going to hit us for another 60 or 70 years, but that's coming too. So there are some really serious problems here. I think we do have them fairly well scoped. Well, let me ask you a question of you, Bob. You said you thought population growth was the big unaddressed issue. I showed a slide that shows the population will in fact peak at the year 2050. I think most people agree on that. Not only that, but if we've been improving our energy use by about 2% per year over the last 50 years. If we keep on doing that, we could all, by the year 2100, have everybody at the European standard of living, and yet be using less energy than we're using today, total. even with Africa and China. So I'm actually very optimistic about the long-term future. I'm much more pessimistic about the next 50 years with global warming. But I don't believe the population issue is the problem anymore. Do you disagree with me on that?
Completely.
He disagrees with me completely. You want to say something?
First of all, do you think that, I mean, most experts agree that, I would actually conclude that Malthus was right, and the only thing we've done to defer the effects of Malthus is we've used technology to increase the carrying capacity of humans, but the fact is that, that you can't increase the carrying capacity of humans on the Earth indefinitely, and what happens is just like these other threshold effects with catastrophic events, you actually yeah, but your data goes back to 1960, and you see it's flattening out there. If you showed me data like that on population, I'm sorry, on global warming, you would discount it as a short-term phenomenon.
But not there's not
the demographic shift is a very recent phenomenon, and you say all experts agree, but I disagree. There's lots of reasons why right now, people that are higher socioeconomic status tend to have fewer kids. That's called the demographic shift. It's not a physical law. There's nothing to say that won't shift again in 20 years. We don't have enough data, actually, to say that that's going to be an important factor
Most
in the future.
professional demographers, including the United Nations,
Because
and most conferences on this. No, these are just some of the data.
Extrapolating from a very short
It's based on much more than that. I'm just showing you the plot that explains why it's happening. Most professional demographers have reached a consensus on this. You may disagree. Just like some people say global warming isn't real. You're welcome to disagree, but you have to at least recognize that the consensus today among demographers is that the population is going to peak in 2050.
Yeah, but the thing is that
It may be wrong.
to not deal with the problem, and if we're already over the carrying capacity of the Earth, so
I never said that we're not going to deal with the problem. I actually pointed out that with energy conservation, we can be using less total energy in the world 100 years from now than we are now, total, with everybody in the world living at the European standard of living. That's good news.
And right now, what is the effect of the human population on species diversity, on habitat?
It's going to peak. We're only going to get to 9 billion.
Right now, in Madagascar, which has the highest level of endemic species in the world, 80%, basically, endemic species means they're found nowhere else in the world. Okay, they have the highest level of endemic species up through the family level. Okay, that means that when you lose the species, when you lose a family level, you've lost an incredible amount of genetic diversity. It would be like losing.
I agree with everything you're saying, but you're not disagreeing with what I say.
No, but the point is that it's being destroyed at a phenomenal rate.
Absolutely.
If we keep it at right where we are now, it's not good enough.
Right, we got to do better. We agree on that. I'm simply saying it's not due to population.
Of course it's due to population.
Not at all. Population is going to peak. No, we have to address those
But
issues.
why are the
but
rainforests? Why are the rainforests being cut down?
Why are the rainforests being cut down? Because it's cheap lumber. Because the wealthy countries are not paying. It's not cheap lumber. It's actually for more farmland.
And why?
Why do they want more farmland? Because they're poor people. The way to stop this is to bring them up to our level of wealth, which we can do without destroying Brazil. But don't think that we have to stop the population. That was Malthus. It turns out not to be true.
But and it's not true because what?
Because the population is going to peak. We're going to peak at 9 billion. It's not going to go up beyond that. And with conservation, with more efficient use, we can actually be using less in the way of resources than we are using today, total, not per person, total. And that means we can afford to leave Brazil. We can afford to leave Madagascar. We can do that, but
it will be gone by
that's up to us.
It's going to be gone. 80%,
yeah, I know.
80% of it is gone.
That will happen, and it's happening because of local population pressure, and because we are not making sure that the local population pressure does not receive the resources that we can afford to give it. That's our fault, but it's not because of population.
Okay, how many people in the room think that population is a problem?
Oh yeah, let's have a vote. This is a good way to determine
science.
science.
You were voting on consensus before.
I was giving you the scientific consensus. I'm talking about the experts. You and I are not experts on this.
It's not true. Well, Berkeley actually has
Be a skeptic.
Berkeley actually has a number of population experts, including Malcolm Potts and Martha Campbell, and they actually are even more extreme than I am.
I can give you the list of scientists who don't believe in global warming, but
Are
there
they
is a
population
consensus. New subject.
Well, all right.
President, and I had both you guys in there. What will I do?
Actually, there really is a procedure for handling that. and the president needs to know it. The president used to have a science advisory committee consisting of top people. These people have to respond to the National Academy of Sciences, which is basically the scientific experts in the nation. The Academy of Sciences will not put out a report without referees. I was a referee on one of these reports on global warming. The process actually does work. No, you don't pick an expert. You don't pick a science advisor, or even a pair of science advisors, and say, now you tell me what's up. No, the process is a much better process than that, and it's been done in the past. It hasn't been done in recent past.
I want to ask a question about the model. Of course, if you believe something about global warming, it's because you believe your model works, that predicts.
It's much more complex than that.
Okay, well, okay, let's make it that simple. Okay. You believe that you have the ability to predict the future from a bunch of equations. I saw the computer once that's supposed to compute this.
But that's not the way I do it.
Well, how do you do it?
Okay, what you do is you have many different approaches, each one analyzing it as best you can. You then look at the data as it develops, and you see which approach is vetted experimentally, which one actually does the work, which ones come out correct. So this is what we do in experimental science. You have many theories. We mentioned a theory about the arrow of time. This is one of the few things we don't do that on. But we have many theories, and then there is a scientific procedure in which you test them.
Okay, at the end, you finally come up with one model that you think is best.
And you have some uncertainty on that based on how well it's worked in its predictive mode.
Yeah, okay, well, the same thing happened with Newton. Newton had a theory of how planets move, and he thought he had the right theory, and you could argue, yeah, Hooke didn't think he did. But of course, you can calculate backwards. And the Newton won that his model worked because he calculated with t equals minus something and saw that it gave the history of the planetary motion.
That's right.
Now, there was a very big event in Earth climate, say 10,000 years ago, called the Ice Age, which actually isn't very long ago at all. If you think about 10,000 years, my God, it's just yesterday. My question is, to test the model that won this scientific contest, can you crank the model backwards and get the Ice Age?
Now, you're aware of the fact that I did write a technical book on the Ice Ages, right?
Yeah.
This is a leading question. Here's the problem with doing that. You're assuming that the mechanism that caused the Ice Age is the same mechanism that's causing global warming today.
No, whatever mechanism, this thing must include all the major mechanisms.
The model.
The physics hasn't changed.
The model, we know the Ice Ages were caused by changes in the orbit of the Earth. That's beyond any reasonable doubt. Okay? And yes, we understand that. It really is caused by changes in the orbit of the Earth.
In a small period of 10,000 years?
Oh, yes, because you've seen this if you've been up to Alaska or the Yukon, and you're there on the first day of spring. Not the first day of spring always, but there's the day when the ice cracks. And in just 24 hours, the rivers go from being frozen over to being running freely because there are instabilities. A similar instability happens at the end of the Ice Age. We believe we understand that. It's a very similar mechanism to the cracking of ice. So that's not a mystery. Okay? However, what's happening now is that we are doing something new that has not happened in 20 million years. Namely, we've pumped carbon dioxide up to a level it has not experienced in 20 million years. Carbon dioxide, in my opinion, was not a major driver during the Ice Ages. So therefore, the models that accounted for the Ice Ages are not the appropriate models for figuring out what's happening now.
Whatever made them was plenty powerful. Maybe the Earth's orbit's still changing, and you
It
ought to
is.
be worrying about that.
No, it changes slow enough. We understand the orbital changes. A new Ice Age is coming. It should occur within 5 or 10,000 years. Global warming, if caused by humans, will be in 50 to 100 years.
We understand all the big concepts in science. We're just filling in the details.
Well, that's of course not what I said, but okay. Next question.
Let's take a question from up there,
Up there.
and then you, sir.
Yes, I believe you said something about 400 years ago, and other people have said 1,000 years ago, that we haven't had the global temperature is as high since those times. So I wonder, how do we know that whatever caused those temperatures to get up to the height they are now aren't causing our current warming rather than humans?
Okay, I actually, the IPCC has analyzed that in some depth, and I've looked at their analysis, and it agrees with I agree with their analysis. They did a very good job. The warming that took place from about 1850 to 1957 does match pretty much a change in the activity of the sun, and it's roughly about what we would expect. That's their basis for saying maybe there's some human effect, we can't say. So they wound up saying nothing about that whatsoever. The first half of global warming was natural. Since 1957, the activity of the sun has started going down. The difference between the warming we're seeing and the activity of the sun is right about what the differential equations predict, based on the understanding of what carbon dioxide in the atmosphere does to the greenhouse effect. It fits very nicely. Even though there's the uncertainty of the water vapor, the other details were filled in with the computer models. And so the fact that understanding up until then the departure of the sun from its previous behavior, and yet the continuing of the warming is fairly compelling evidence. It's not absolutely certain. They only say it's very likely. They don't say it's clear and incontrovertible. They say it's very likely. The words are chosen very carefully.
Okay, thanks very much.
And for the last question of Wonderfest 2008.
The topic was on presidents and what they should know. We've had a party that's put some presidents in office recently that believe in astrology, that believe that cavemen walked around with dinosaurs, that said the jury's still out on evolution, and I think we have a vice presidential candidate that believes the Earth is about 4,000 years old. And the problem is that the American people, a large majority of them, all agree with this. I question if scientists aren't doing their job in making sure that people really understand some of these things. Because I argue with people, and I say, I would never hire an engineer, that had those beliefs. But, why not? I have those beliefs. And I think we have a real problem here. Obviously, if you believe that the Earth is only 4,000 years old, a lot of these things you bring up is totally irrelevant to someone. If they're in charge, we're in a lot of trouble.
No, I agree with that statement, and may I respond, please?
Carl Sagan said that if the president went into Kuwait, the oil wells would be burnt, and we would have a nuclear winter. And we went into Kuwait, kicked the ball out, and we didn't have a nuclear winter. But Carl Sagan is still up here as a hero.
My response to your comment is that I think a large part of the fault is scientists. I think we physicists in particular have been raising new physicists. We have not been educating the public. Carl Sagan is one of my heroes for just that reason. So we need to get that education out. I think we teach physics in a very arrogant way. We say, if you can't understand the math, then you can't learn the physics, too bad. And I also think that physicists have made a mistake in recent years in becoming public advocates. They have a spin. I know many, many of my friends who listen to my talk and they say, well, everything you say about global warming is absolutely right, but you shouldn't say things like that because you make it seem less dangerous than it is, and that will mislead the public into not being worried about it, so you should put some spin on it. And there are some very, very famous scientists, you know their names, I'm not going to say them, who tell me this in private. So I believe that once we start spinning things because we have an agenda, because we think this is a problem and the people have to worry about that, then we lose our credibility. And we talk about the trust that scientists had after World War II. I think we've largely lost that now, and that's part of the problem. And it's because we have a political agenda too, and we have to be able to give advice without putting spin on it.
I'd like to comment on both. Possibly on both the question and the answer. I'm actually a science educator. I actually don't think the problem is the scientists per se. The reason for that is that the job of the scientists is to do science. And the fact is that the reason why you can put the science out there and it just turns everybody off because they don't have any science education. They don't have any science education because of the policymakers who don't. The science education has to be a lifelong process. You don't decide that you're going to be a scientist when you're 18 years old. You have to have this sort of upbringing that allows you to be amenable to scientific thinking. If you're already indoctrinated, it becomes very, very difficult. So I think the issue is at the level of the leaders. I think that Tucker was right on in sort of posing the problem. And I do think that it's one thing, of course we should tell the truth, of course we shouldn't give a spin, but the fact is that most of the public is not in a position to be able to understand they can't be informed consent. And in fact, going back to the doctor analogy, I know a lot about medicine, and the bottom line is when I go to the doctor, I say, how many cases of this have you seen? What would you do if you were in my position? Because if it's not directly in my field, there's no way that I can have the knowledge to actually even process the information. So we're reliant on those experts.
Okay. Thank you both very much. Wonderfest will now come to a close. Please join me in thanking Professors Muller and Siegel, and also let's thank Tucker Hyatt for the incredible job he's been doing for the last 10 years on Wonderfest. If you've enjoyed this weekend's events and talks, please pop a donation in the white box over there, and I think there's some out in the lobby as well, I think.